Recording. Yeah, recording has started. Good. Let me now share my screen. Okay, I hope it is visible to everybody.
Yes, sir.
Oh, okay. Okay, then I will switch to the chat version. Okay. Okay, good. So this was a problem which I mentioned a bit difficult, but solvable with your knowledge. I actually have received a correct solution by email. Anyway, let us not waste too much time on this exercise because it is a little bit tricky. So let me solve it. If you have tried it yourself and solved, it's fine. Otherwise, just look at the solution. We will move to induction soon. Okay, so the hypothesis is that GCD of A and B is 1. So I can write A as a product of primes, P1 alpha 1, P2 alpha 2, PR alpha R. Okay, and I can also write B as a product of primes, let's say Q1 beta 1, Q2 beta 2, blah blah blah, QR maybe, sorry, QS beta S. Given the condition that GCD of A and B is 1, it has to be that these primes P1, P2, PR, they are all distinct from Q1, Q2, QS. Okay. Okay. So PI, QJ, they are distinct. Okay. So now I look at C. Nothing is mentioned about C. So C may have some of these factors P1, P2, PR. It may have some factors Q1, Q2, QS common to B. And it may also have its own private factors. So I write it this way. Gamma 1, P2 gamma 2, PR gamma R, where these gamma i's are not necessarily positive, they may be 0. If some gamma like gamma 2 is positive, this means that C has some prime factor P2. Okay. We allow this to be, these exponents to be 0 also. And likewise, it may have some prime factors. QS, delta S, and finally, here also this delta J's are allowed to be 0. Just in case, for example, Q1 is not present in C, in that case I take delta 1 equal to 0. This is allowed. And what about this? It's private prime factor. So this may be something like R1 power what? So alpha, beta, gamma, delta, this is going like coronavirus. So anyway, let us call them epsilon 1, R2 epsilon 2, RT epsilon T. Okay, where these primes Rk are distinct from Pi and Qj. Okay, so this is a kind of constructive proof. I am suggesting that if I take this product, R1 power epsilon, R2 power epsilon, epsilon 1, R2 power epsilon 2, R3 power epsilon t as x, this will work. So you note that this C may have no such private factors. Okay. It may even be 1. Okay. So in that case, what will x be? So t is 0. What is x in that case?
1.
1, right? So never forget this thing. An empty product is always 1. What about an empty sum?
0.
0. Great. What is an empty, let's say, min?
Infinite.
Which infinity? Plus or minus?
Plus infinity.
Plus infinity. And an empty max is minus infinity, right? So never forget these things.
Sir, how empty min is plus infinity? Why will it be minimum? Or
Why? So there you say, if I am going to take a minimum of certain things, and if I initialize that min variable to something finite, okay, not plus infinity, then if I consider that next number, okay, now the point is that if it is not plus infinity, it is something smaller than plus infinity. Okay, I initialized min to something smaller than plus infinity. Okay. So now since this is smaller than plus infinity, the next element that comes for the comparison may be larger than this initial value. Yes or no? It's possible, right?
yes.
Okay. And in that case, if I make the comparison, if the new value is less than mean, then mean is that new value. So that's the standard programming, right? And that condition will fail. The only number for which the next value can be correctly captured, the only initializing value is plus infinity. You convince yourself. If I do anything other than this, I may make an error in the next step. Convinced?
Yes.
Okay, good. Okay. So what remains is to show that this x will work. Okay, why? Now I am considering GCD of something with C. So the GCD will have prime factors, these or these or this, because C is involved as one argument. Okay. And one by one you show that by the choice of this X, neither of these PIs, nor these QJs, nor these RKs can be a divisor of A plus BX. Why? Maybe let us quickly look at it. So P1, for example, it is divisible by, it divides A by the construction of A, by the choice of this P1 or P2 or whatever, divides A. But it does not divide B because A and B are co-prime. It also does not divide X because X is different from these primes and these primes also. Therefore, this is divisible by Pi. This is not divisible by Pi. Therefore, the sum is not divisible by Pi. So, in this GCD, no Pi will come. Similarly, you show that no QJ will come, no RK will come. Okay. Happy? Because if I look at a Qi, it is not.
Sir, even if we choose,
Tell.
sir, even if we choose X as a as a product of none of the PIs, QIs, and RIs, then also it will satisfy. Uh, the X should be the one of the RI.
You take X to be anything other than this PY, QI, RJ.
Yes, sir.
Let me see. Maybe you take some other prime S. Okay, I have already used R here, R here. So don't get confused. These are R1, R2, and this is R. The notation is quite complicated. Anyway, if I take S to be any other prime, how do you guarantee? So S does not divide A because you have chosen something like a brand new prime. S does not divide B, S does not divide X, but how will you guarantee that S will not divide A plus BX? Oh,
Sir, but even if X divides S divides A plus BX, S will not divide C.
S will not give, no, it's not the question of S. You have taken X as S, something different. See, I am considering this. Okay. So you have to eliminate that P1 cannot appear here, Qj cannot appear here, Rk cannot appear here. P1 will not, P1, P2, these Pi's will not appear here, Qj's will not appear here. But how will you establish that this sum is not divisible by some R? How do you establish that? Let's consider R1. R1 does not divide A. R1 does not divide B plus BS. But A plus BS may be divisible by R1. So these factors might come in the GCD, right?
Sir, I have a counter example, sir.
You can find a counter example. This will not work. Yeah. It's fairly straightforward to come up with a counter example. So this will not work. Whereas if you take X this way, it will work. Probably it will work.
Sir?
Yeah.
Sir, we can take Q also. Yes, sir.
Huh?
We could take Q's factor in X also. X could contain R's and Q's also. Yes, sir.
Possibly that will also work, but that will work. Yeah.
Yes.
A plus BX. BX will have those Q's, but A will not. Yeah, that will perhaps also work. Yeah, that looks like fine. Yeah, good. So you have given a counter example. Yes, it's possible. Yeah, nothing prevents this from happening. Okay. Yeah, so QI, so it will not be here, it will be here. Yeah, you can also include, I think, this part also in X. Yeah. Anyway, so this is, you understand, this is a kind of constructive proof. Okay. Anyway, so if you do not have any questions on this, let us actually go to induction. Yeah.
Sir, here in this question, it is written that for term x belongs to n. Sir, which means, is it sufficient to give one example to prove this thing?
No. Look at this is the for all. This is a for all ABC statement, right? So you have to take any A, B, and C, and given its hypothesis that GCD of AB is 1, you construct an X, either prove an existence, or if you can explicitly construct X like this, it is fine. Okay, but you have to prove it for any arbitrary A, B, and C. Starting with the assumption that they are co-prime, A and B are co-prime. And now this is their existence. Any X in a constructive manner or existential manner, you can prove it. Okay. Happy?
Yes, sir.
So after construction, do you have to write something to prove that this construction is true? Means if it comes in exam, then what exactly should I write?
No, I have not used any example. This is a generic construction, right? This follows from the fundamental theorem of arithmetic that every integer can be written as a product of primes. This theorem, of course, I have used. This is a well-known theorem. That's why I think we can use it.
Now about the value of x, should we write something after the construction to prove that
No.
this?
First of all, you can factor numbers, right? Efficiently or non-efficiently, let's not worry too much about it for the moment, but you can factor numbers. So you can compute this factorization, you can compute this factorization, you can compute this factorization. And then just take out these PIs, Qj's from the factorization of C. Whatever remains, you call it X.
Yes.
Okay, so in a programmatic sense, this is constructive. You can write a program for this. Yes or no?
Yes, I can write.
Okay.
Sir,
Yeah.
so the doubt was like basically in terms of writing solution for an exam. So if this comes in the exam and we suppose take X as this and like we write this proof. So are we supposed to explain in further 2-3 lines that why taking this X gives us this answer and all, or like is it considered understood and all?
No. First of all, what I didn't write to save time and space
Yes, sir.
is that why this X will work.
So sir, in exam we are supposed to, like we are expected to explain.
Yeah, supposed to write little bit.
Yes. Yes.
Why this is why I mentioned verbally, right? Why some PI cannot be a factor of this.
Yes, sir.
Common factor of this and this.
Yes.
Likewise, you show why Qj is not a common factor of this and this, and no Rk is a common factor of this and this. This much you should write.
Yes.
Okay.
Sir.
In order to complete the proof. Okay.
So can we write symbols or we shall write sentences, long sentences?
I didn't understand.
So for some expression we can write in symbols like A divides B. We can write in other way instead of writing.
Whatever is understandable to the human reader, that is fine.
Can you use some normal external theorems?
Yes, please. So write why these do not divide A plus B. So this step I have just mentioned verbally, you should write. Yeah, then what is the question?
Can I use some extra theorems from outside, like the one I posted? Normal
X
theorem.
plus Y is co-prime to Z if the prime factors of Z divide either X or Y but not both. Is it a really common theorem?
This one is used in making the constructive proof.
Yeah, that is true, but better mention it, complete it. Of course, I am not expecting you to prove this fundamental theorem of arithmetic. That is difficult. But otherwise, whatever you are writing here, it's essentially doing something like this. this argument. So better do not use external theorems which are not proved in the class. Okay.
Sir.
Unless things like this prime factorization, and I believe we will actually prove this fundamental theorem of arithmetic. We will actually prove it in a later lecture, but yeah, here we are using it. Anyway, you look at this. This is already a starred exercise. Possibly we will not give you such starred exercises in your exams. Okay, so unstarred exercises you should be able to solve yourself. Fine. Let us go to induction. Let us not worry too much about this exercise. Let us go to induction then. We're already halfway through. Okay. I received only one query. What if induction involves two variables? How do I proceed? So one possibility was already covered here. Here it's induction on M and N. Okay, so one possibility is that you do something like this. First prove that 0, 0 is in S, and then you assume that some M, N is in S. Prove that M plus 1, N is in S, and M, N plus 1 is in S. Then this will show that this S consists of every pair of N naught product N naught or something like that. Okay, so this is one possibility. And second thing is that in some cases, actually you do not have to have these two induction steps. From here you show this and this. It sometimes suffices to consider any M and proceed by induction on N, or you consider any N, you fix any N, and then proceed by induction on N. Okay, so this is another way, and this is what we will do in our next exam. Yeah, so this is an example of induction involving two variables M and N, and it is you are supposed to prove that for all integers with M greater than equal to 1 and N greater than equal to 0, this identity holds. Now, if I want to proceed in that generic way, I have to show that something like if this holds for Mn, it also holds for N plus 1. It also holds for M plus 1, N, something like that. But it is not needed to do it this way for this exercise. You can do induction on M or induction on N. You can also prove this by induction on M plus N. A single induction will do actually. So that M plus N thing I do not want to cover here because it involves multiple cases. I will proceed by induction on M or N. Which one do you like?
M.
M? The first
Yes,
one?
sir.
Okay. So I will do induction on N. So you try induction on N. Okay. So when I do induction on M, I take N arbitrary. Take any arbitrary N. We are not putting any value like 0 or 1 or 2. And let us try to see whether we can still establish this assertion. You take any fixed N but arbitrary. Okay. It can be anything but fixed. So what is the basis? see that m starts from 1. So m equal to 1. So plug in f, this is 1 plus n. Now whatever n you take, okay, whatever n you take, any n greater than equal to 0, it doesn't matter. I can write it as fn plus 1 times this, 0 times fn. Right, fn plus 1 and fn are both defined for any arbitrary n greater than equal to 0. Happy or not?
Yes, sir.
Okay. But you see that f1 is nothing but f1, n plus 1, f0, fn, and for the case n equal to 1, this is fm, fn plus 1, this is fm minus 1, fn. Happy?
Yes, sir.
Okay. I see. Now, okay. So how many basis cases you should consider?
So 2.
2, right? Because eventually
Yes.
I have to use this Fibonacci recurrence in the inductive step. So I need another case, m equal to 2. So f2 plus n. Again, irrespective of whatever the value of n is, this is fn plus 1 plus fn. And this is 1 times fn plus 1 times fn. This is nothing but f2. This one is f1. So once again I have fn plus 1 plus fm minus 1 fn. Happy? Okay.
Yes, sir. Then I have to proceed by induction. So I will assume that, okay, what was the formula? If m plus n was m n plus 1 and m minus 1 n. This is true. I will also assume this is true for m plus 1. Okay. So this is the induction hypothesis. I have to prove this statement for m plus 2. How do I proceed?
Sir, we
So we
need
will
to
add
prove
these
the
two.
second statement, right?
Simply I add
M
this
plus 2.
and use the Fibonacci identity. It will become fm plus 2 plus n. Here I will take fn plus 1 common, whatever it is, fm plus 1, this will come to fm plus 2, fn plus 1. Here, add this and this, I will get m plus 1, fn. So this is m plus 2, and this is m plus 2 minus 1. Happy? So here I do not worry about what the exact value of n is, irrespective of whatever n is. This manipulations never use something like It always uses Fn, Fn plus 1, which are always defined. Happy?
Yes, sir.
Okay. And I hope the question raised in the query is somewhat answered with this example. Okay, so this is a case where actually I do not do something generic like this using two inductions, but a single induction suffices. Okay. In fact, the next one is also interesting. M divides N implies Fm divides Fn. So once again, this involves two variables M and N. So we will proceed by induction on what?
Sir, we can proceed via induction on M by N. Sorry, N by M.
N by M, yes. Okay. So it's now actually a third thing on which we are applying induction. Okay, so since the hypothesis that is that M divides N, so I can write N as Q by M. And then proceed by induction on Q. What is the basis case? Of course, if M
Q
and
plus
N
1.
are positive, yeah, if M and N are positive, then there is Q cannot be 0. Okay. So basis case is Q equal to 1. But if Q is equal to 1, this means M is equal to N, and therefore Fm is equal to Fm, and therefore Fm divides Fm. So this is obvious.
Sir,
Yeah. Yeah,
should
tell.
we take M equal to Qn or N equal to Qn?
M divides N. So N is a multiple of M. So this symbol is actually divides. Okay.
Yes, sir.
Okay.
So Q can be 0 because we can take N equals to Q and N equals
Let
to
us assume that M and N are positive. N0 case is not. So this is how this exercise is given. It can be 0 also. Anyway, in that case, N is 0. Yeah. But here I have assumed that they are positive. Okay. That's why I start with Q equal to 1. And what is the inductive step? So let's say Q greater than 1 and Fm divides F Q minus 1 M. I have to show that Fm divides FQM. How do you do?
Sir, we can use the previous identity.
Yes, sir.
Oh.
Yes, sir. We can use the previous
Yeah.
that we have proved.
Here I will use M. Here I will use my, right? So you see that this is already a multiple of Fm. Whatever this is a multiple of Fm. And by induction, this is a multiple of Fm. Happy or not? So this term is a multiple of Fm. This term is also a multiple of Fm. This is because you can see Fm. This is because of the induction hypothesis. So their sum will be a multiple of Fm again. Okay. So now use part A. with m equal to m, n equal to q minus 1 m. Happy? Yes or no?
Yes, sir.
Oh. So now let us ask the question. Is it true?
So can we use the
Huh?
induction step? Right? We directly proceed. Here we did not use the induction step. Fm divides fq minus 1m. We did not use that step. I mean, to prove the further fm divides fqm.
Now, what do you think? This is true or not?
Yes, sir, that is true, but I didn't get the purpose of induction step in this proof.
Induction is this. This is, you can see, it's a multiple of Fm. Induction hypothesis is that Fm divides this quantity. So, but that quantity n is nothing but q minus 1 times m. So, this is a multiple of Fm, that is induction hypothesis. Whatever this is, doesn't matter. This is another integer, this is another integer, this is equal to Fm. And the induction hypothesis is that this is a multiple of Fm. Therefore, the sum is a multiple of Fm. Yes or no?
Yes.
Yes?
Yes, sir.
Okay. Okay, so
But sir, the sum also means okay, sir, understood. Yes.
okay, yeah. Okay, so what about the converse?
So this is not true.
This is not true?
Sir, I have a counter example. Assume that m is equals to 2 and n equals to 1.
Okay. Okay, so this is actually not true, and you can prove it by providing a counter example. So you note that f2 is 1, right? f0 is 0, f1 is 1, f2 is also 0 plus 1, 1. That divides something like, as you mentioned, f1, which is also 1. Okay. But this does not imply two does not divide 1. Okay, so this is false.
Yeah, but beyond 2, we see that there are no examples like this.
Beyond 2, there are no examples. Okay, try to prove it or disprove it. Let us see. Okay, so we'll do this offline. Beyond 2, is it possible? Is this a correct statement or not? Assume that m comma n are greater than or equal to 3 or something like that. Can you prove this? Okay, so you will try it offline. We will see. Okay, so let us look at some other example. Oops. Maybe this is not so difficult. Okay, let us do it. Maybe I have to skip 1 or 2 examples. The last one I would like to cover. This is actually fairly straightforward.
Sir, we can write that, sir, 2 to the power n log base 2n to be n to the power n, right?
N to the power n, right? This side is n to the power n. Yeah. And then it's just a matter of manipulation. So I just write it. We will spend some time on the next exercise. So n equal to 4 basis. Okay, so let me write it this way. 2 power n less than factorial n
less than n power n, because this is same as n power n. So basis n equal to 4. 4 factorial is 24. This is definitely less than greater than 16, and less than 4 power 4 is how much? 256. Okay. So assume that for some n, this is true. Okay, so what do I do? N plus 1 for some n greater than equal to 4, and I have to prove it for the next one. So what is n plus 1 factorial? This is n plus 1 times n factorial. Okay, on the one hand, by induction hypothesis, this quantity is bigger than 2 power n. This is n plus 1. Since n is greater than equal to 4, n plus 1 is sufficiently larger than 2. So this is greater than 2 times 2 power n equal to 2 power n plus 1. This establishes this side of the inequality. The other side, this is also quite easy. I know this is less than equal to, okay, equal to n plus 1 times n factorial. This is less than n plus 1, n to the power n, which is definitely less than n plus 1, n plus 1 to the power n, which is equal to n plus 1 power n plus 1. Okay. So you can prove using other methods also, but this is a pure inductive proof. For example, if n is sufficiently large, it's a product of 1 times 2 times 3 up to n. 1 is less than n, 2 is less than n, 3 is less than n, and so on. So the product will be less than n to the power n. This is another way of arguing. But this is an inductive establishment of these inequalities. Happy or not?
Sir?
Yeah.
Sir, if this question comes in exam and we write similar solution without writing any statements, will it be sufficient? Or we shall write that this is less than, definitely less than n plus 1 times n plus 1 to the power n, like that.
Yeah, you say the steps, right? This is a very simple example, but somehow you have to arrive at this inequality, right? This side
Sir,
you have.
I'm
Then
asking that submission, do we need to write the statements explaining those steps? Or is it sufficient to write those steps?
Which steps?
The steps which you wrote now, I mean, basis.
Yeah, yes. To show this, right?
Yes, sir. We will write everything on this which you wrote, but do we need to anything extra, some statements?
Because I am telling something, right? So for example, here you show, here you write because n plus 1 is greater than 2. Something like that. Why you are using this? Okay. Because in the class, I always say things like, but here, of course, you do not have to say anything because I can see n is less than n plus 1. Okay, so here you don't have to write n less than n plus 1. This is more or less obvious. So whatever you think is needed for completing your solution, do it. Here, maybe it's a good thing to write by induction hypothesis. This equality. This follows from the induction hypothesis, right? Okay.
Yes.
Okay. So since I am talking, so I am not writing all the things. Anyway. So whichever the key steps you use, write. It's preferable to write.
Okay. So maybe we just have a time for another exercise. Anyway, I will provide a solution to this problem. Let us not do it. Let us do this. I have a reason to cover this.
So can we use a strong induction in this case?
Yeah, we will raise everything to power n, right?
Yes, sir. Like we can give a base case here that is n equals to 1 for that we get 2, that is an integer. Then we'll assume that up to Sn they are all are true. Then x to the power n plus 1 upon x to the power n equals to some q or p, anything. Then we can multiply x to the power n plus 1 upon x to the power n with x plus 1 upon x.
Oh, okay. So, okay, I got your point. I got your point. Okay, and then with some jugglery, you will come up with.
Yes, sir.
Okay, good. So that's not a bad thing. Of course, you can also do by raising this x plus 1 over x whole power n and then using the properties of binomial coefficients. But whatever you are suggesting is somewhat neater. Okay. So what I will do, I multiply this with the previous one. Okay, it is true for n equal to 1. Okay. So that is actually the hypothesis of the exercise. But anyway, let's see. If I multiply these two things, what will be the result? This x power n, this 1 over x power n, plus this, or maybe this, and this. So if I make a slight rewriting, this is nothing but this quantity, minus happy?
Yes, sir.
Now this is given to be an integer. This is the original thing. The previous one is an integer. The previous to previous one is an integer. So this has to be an integer. So now the question is, how many basis cases do we have to solve? Two, right?
Yes, sir.
Because this depends on previous one and previous to previous one. So 2 basis cases should be there, and this is the reason I wanted to highlight this. N equal to 1, this is given. X to the power n plus 1 by x to the power n. This is 1, so whatever, 1. So this is already given to be an integer. Then we need something like for n equal to 2. This is needed, right?
Yes.
Okay. So I simply, this time it's easy. Whole square, x square plus 1 over x square plus 2. Now x plus 1 by x is an integer, its square is an integer, subtract 2 from it, it will remain an integer. So this is true. Happy?
Yes, sir.
Yes, sir.
Okay. So the question that I raise, what
if we proceed by strong induction, the idea is this. I assume that this is true for 1, 2, 3 up to n minus 1. Okay. Proof for n or 1 to n up to n plus 1. In a typical proof like this, how many basis cases do you handle?
Sir, only one.
Only one. So here also I can assume the same thing. So this is the case n equal to 1, this is the case n minus 1, and I am also using n minus 2. So do I really require two basis cases? Okay, so in such a proof, only one basis case is necessary. So why did I do 2?
Sir, because n minus 2 may not lie in the range 1 to n minus 1 if n equals 2. So, sir, we are getting the same problem as the horse problem.
Exactly. So that is the idea. For n equal to 2, this n minus 2 will no longer remain in this range. It turns out that x power 0 plus 1 over x power 0 is 1 plus 1, which is 2. It is true for n equal to 0. Okay. But the inductive proof has a flaw. And it is exactly similar to that horse case. All horses are of the same color. Okay. So actually we need two cases. Unless you prove it starting from 0. Okay, even starting from 0 means this 0 minus 1 minus 2 may become minus 1. So again, that is true. 1 by x plus x. Yeah. So actually we need two basis cases. Are you convinced?
So, sir, we can proceed by strong induction, but just that we need to write an extra step to prove for 0.
There is an extra step to prove for 0. Yes. So in any case, we need two basis cases. Prove it for 0 and 1 or 1 and 2 as we have done here. Okay. So two basis cases are needed, right? So be careful. Be careful. So otherwise you will end up in that all horses are of the same color case. Good. Okay, so I would suggest that we stop here. This one is fairly straightforward, so you can simply compute it. And I will post it with solutions maybe within half an hour or so. So let us see whether you have any questions regarding this tutorial session, or for that matter with the exam tomorrow.
Sir, we are having syllabus till the first part of this week.
Yeah, up to induction. Up to induction.
So, sir, till the first video of this week.
Yes, yes. After this, we have done something like recursive constructions, blah blah blah. All these things we will not ask.
Okay.
But this kind of inductive proofs you should be able to handle. Yeah. So, any questions on the logistics? Are you comfortable?
You said at the last for strong induction case?
No, I didn't hear it.
So at the last, what did you say for the strong induction case?
This one you can do strong induction or the special case of induction where you use two previous values. Okay. And these are examples which is just a weak case. We just assume the previous one. This is an example where this part B just assume the previous one, but part A assume the two previous things. Okay. Maybe we could have covered one example where we have used everything. Anyway, so
In particular, if you have any question on the logistics of tomorrow's test, please let us know. Have you tried taking a scan and preparing PDF? Have you tried it?
Yes, sir.
Yes.
So just one point, that only handwritten submissions will be there. Either you handwrite in computer directly through digital pen and save it and upload, or you handwrite in piece of paper, scan it and send. But no typed answers, saving as a Word document or a PDF and directly sharing the typed answer, keyboard type, we will not accept it. Okay. And remember the time, it's 1 hour plus 15 minutes for everything that you suffer from, like doing this, that, network issues and all. So even if you are 1 minute late than that, we cannot take it, because the server will automatically, we will keep it closed. If you are 1 minute late, remember you are not 1 minute late, you are 16 minutes late. Okay, just remember that.
So can we get a model solution as to how we will write the answer?
So that a human can read. It is not an automatic evaluation. Suppose you sit in the exam hall and write an exam and then give it to the examiner to evaluate. Yeah. Human manually will check. He or she should understand and should and give you marks.
Okay, sir.
So I think Professor AD today also mentioned that if something non-trivial you are trying to do, just try to prove it, or if something you are assuming, write it and then go for your solution. Suppose that n less than n plus 1 you do not have to write, but why this 2 to the power n becomes 2 to the power n plus 1, you make a statement for that. So that a human can follow your steps. That's it. Okay. Don't get afraid. I know you all can do it very easily. You have done it in the past. Just whatever you think, you write.
This is yet another exam.
Yet another exam.
You just take it as a maths exam. So little bit rigor is expected. That's the only difference.
Whatever you think, you write it. Do not step jump too much, because see, our machines are Pentium machines, your machines are i9s. So do not step jump too much that you assume something, directly derive something we cannot follow. Whatever you think, you just write. Okay.
So can you tell how many questions will be there?
Arey, yaar, 1 hour, how many you can answer, you answer. Do not think about that too much. Why are you taking pressure? How many questions? If I tell 10 and if I tell 2, how does it matter? You prepare, you will do well. Do not take so much pressure in the marks and numbers of questions. You are good students. You will do anyway well. You just prepare. Okay.
Okay, sir.
Not happy, right? See, we will give you those many number of questions that you can at least solve in 1 hour. It is not too absurd to solve in 1 hour. Okay.
And
okay, all the best.
Complexity will be unstarred, I would say. Not the starred exercises.
Yes, obviously.
Yeah.
Unstarred are for your, that is your food for thought. Starred, unstarred exercises are, we will follow those. Okay, difficulty wise. Any other questions? All right, I think we can close.
Okay, so see you tomorrow.
Thank you, all the best. See you tomorrow.
Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.